watching 3M Science at Home.
I'm Angela Kalopisis. I'm a grade 6 student and I love science. This is my mom.
I'm Tina Kalopisis. I began my career at 3M 18 years ago after completing an honors degree in genetics and a master's degree in computer science. I'm very passionate about encouraging the next generation of students to pursue studies in science, technology, engineering, and math. The career possibilities are endless. In my own career, my science degrees have taken me from being a software developer to a business leader to a lab manager and to my current role of working with an amazing group of scientists in healthcare regulatory and quality affairs. I've always had an interest in science, and when I was younger, I would watch documentaries on bridge construction. There are so many incredible bridges around the world. So far, we have taken Angela to see the Brooklyn Bridge and my personal favorite, the Golden Gate Bridge. So today, welcome to our kitchen table, and let's get started on our 3M Science at Home bridge experiment.
If you've ever looked at bridges, you've probably noticed that they can be made of different materials. Some are made of wood, steel, concrete, or even stone. But what materials should engineers use to build a bridge? Different materials have different properties called mechanical properties. For example, how hard is the material to stretch or bend? When you bend the material and let go, does it stay bent or go back to its original shape?
And if you bend the material and it breaks, does it happen slowly or snap suddenly? You can probably imagine that the properties will be important for a bridge.
If a truck drives over the bridge, do you want the bridge to sag? Should the bridge return to its original shape after the truck leaves?
Well, in today's activity, you're going to explore these properties with various household items and decide which one would make the best bridge. So, our first step is always safety. You often see scientists wearing safety glasses or gloves, particularly when dealing with volatile chemicals and extreme temperatures. But today, since we're working with generally safe materials, I don't think we're going to need any gloves. But I always have my safety glasses on.
And make sure you have an adult on hand to help you out.
All right, so to get started, you're going to need several thick books or small boxes. We are using some of our cooking books today. You're going to need some paper, wax paper, aluminum foil, some scissors, tape, and at least 25 pennies. Or you can always use another heavy coin like quarters, which is what we're using today. So first, we'd like you to cut your wax paper and aluminum foil sheets the same size as the piece of paper. We've already pre-done this for today's experiment. Space your books approximately 10 inches apart. And then fold each of them into half, and then half again. And then, of course, every bridge needs some guardrails, so let's make sure that it's wide enough to hold the quarters when they're sitting flat. But put some guardrails on. Great, and then to make sure that our bridge doesn't lose its shape throughout the experiment, we're going to add some tape to each side. So as we're doing this, maybe you could think, which material is going to lead to the strongest bridge? All right, so now we're going to rest our bridge in between our books, just like this. And now I'm going to ask Angela to add quarters on one at a time in a row along the bridge. So 1,
2, 3, 4, 5.
So watch the bridge as you add more quarters. Does it start to sag? And once you fill up the first row, feel free to make it a second level as well.
26, 27, 28,
No.
29, 30, 31.
Oh, there it goes.
Oh, it's 33, 32, 33, 34, 35.
Oh, 35. Okay, so we got 35 quarters on the paper bridge. So now you'd want to repeat this experiment with the tin foil as well as the wax paper. And maybe you're going to be surprised by which bridge is actually the strongest. So now that we've completed our paper bridge, now we're going to move on to the next material. So we're going to try and make a bridge out of wax paper. Again, the wax paper, we cut it to the same size as the paper bridge. And so Angela's going to fold it in half and half again and make some tight seams on it so it doesn't fall apart. And then she's going to put up the guardrails again. And remember, please keep it as wide as you need in order for the currency that you're going to be putting on the bridge. So for us, it's going to be quarters. We're going to tape the edge to make sure that it doesn't fall apart. Okay, good job. All right, so now let's position our bridge between the cookbooks. All right, so let's start adding quarters and see how long it takes for this bridge to fail. 1, 2, 3. Oh, 3! Okay, well that was significantly fewer quarters than in our paper bridge. So should we try metal next?
Yes.
Okay, so let's do tin foil next. Okay, go ahead. So again, same size as the 8.5 by 11 piece of paper. We're going to fold it in half as best you can. Fold it again in half. Put up the guardrails, ensuring you have enough room for your currency to sit in the middle. And make sure those edges are pretty tight, or else it looks a bit like a canoe. We're going to tape it so that it doesn't fall apart. We conduct our experiment. Now, I wonder, what do you think is going to happen? So most bridges, I think, are made out of metal, so I'm going to expect that this one's pretty strong.
Yeah.
Okay, so it's in position. There we go. Make sure it's wide enough for our quarters. 1, 2, 3, 4, 5. Oh, 5. Okay, so that failed at 5. Wow. So if you want to take this experiment a step further, you can try something like building a new bridge from each type of material and adding the quarters to the bridge, but not enough to make it collapse. Then try removing the quarters and take a look at the bridge. Does your paper or tinfoil bridge completely return to its original shape, or is it permanently deformed? Secondarily, you can also take a look at the shape of the object and understand that it affects its strength. Try changing the geometry of your bridge. For example, the width of the bottom and the height of the walls. And how does changing that shape affect how many quarters the bridge can hold?
You probably found out that paper made the strongest bridge, and you might have been surprised that the aluminum foil bridge wasn't the strongest. After all, isn't metal stronger than paper?
An object's strength depends not just on its material, but also on its dimensions. A thick piece of paper, for instance, can be harder to bend than a thin piece of metal, such as aluminum foil.
You may have also noticed that the bridge did not all collapse the same way. The paper bridge may have started to sag gradually, while the aluminum foil and wax paper bridges may have failed much more suddenly.
So, how do you take this information into account when building a bridge of your own? I'm sure there are so many things that you can consider.
Remember to clean up when you are done by disposing of or recycling your materials.
So, thank you so much for watching. I'm Tina Kalopisis.
And I'm Angela Kalopisis.
We hope you check out more Science at Home videos from 3M.